Good afternoon. Marshall Porterfield is a professor of biological engineering at Purdue, where his research focuses on biosystems in the space flight environment for developing the development of biomedical countermeasures and bioregenerative life support technologies. He recently served NASA as Division Director for Space Life and Physical Science, including human research and space biology programs focused on science for the human exploration using the International Space Station. During his tenure, he developed a new open science paradigm for the utilization of the ISS. Today, he will present a talk titled Space Exploration and Technology for a Sustainable Human Civilization. Please take a moment to silence all of your cell phones, but keep them out. We'd like you live tweeting this at the hashtag Dawn or Doom. Thank you.
Good afternoon and welcome. Thanks to the organizers for the opportunity to talk today. It's been about a year since I've been back on campus at Purdue, and I'm really enjoying being back in this great environment, working with students again, and also I'm very happy not to be in Washington, D.C. anymore. So let's start off. I want this is just to set the stage. My perspectives on human space exploration, humanity in general. This is a great quote from Carl Sagan, one of the really American treasure in science. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there's no hint that help will come from elsewhere to save us from ourselves. That's very true. We are literally, as far as we know, alone in this universe. There's no one that can help us other than ourselves. So the first step in solving problems is identifying that there is a problem. So as we start looking at, sorry, I'm getting used to the controls here. Our home, the home planet, Earth. We know that there's probably, by most conservative estimations, there's life out there in the universe. So everything we've learned about life on this planet, life in extreme environments, the basic chemistry of life, we can project that out. The Hubble, the telescope missions identifying Earth-like planets and planets in habitable zones around planets. There's probably other life out there, but space is so vast that we are essentially alone. This is our home. This is the birthplace, the cradle of humanity. All the science, all the technology, everything that's good, art, literature, everything that's beautiful about humanity and the human experience comes from the planet Earth. Is this going to be the final home for humanity? Are we going to persist here and survive? Or are we going to thrive and expand the human presence out into the solar system and potentially beyond? So I think it's important to understand my perspectives on space exploration also stem from the study of anthropology and archaeology and understanding the early stages of human evolution. And why are we like we are today, creating this crazy technology and this explosion of science that's happening around us? What's the impact of that? Where does that come from? What drives us to explore? These are foundational questions. I think it's really important to consider that when we think about space exploration and our future. If you look at the early colonization of a planet by a species, that's what we're in the middle of experiencing right now, the last 100 to 200 years. If you look how far we've come in a short period of time and the impact of technology and science in driving that. It all started in Africa and the early hominids exploring, building tools, figuring out what was over the next hill was a better hunting grounds. If you were curious and you moved out and you explored, you found new lands. Your genes persisted. Humans evolved, and we selected for these types of traits. We were tool builders. We solved problems. We first learned how to use fire and later how to control it. We learned how to build tools to aid us in our life, but also in our exploration. Exploration and technology and science are all intermingled in a very intimate way. And I think it's really important to keep these things in mind. when we start considering what the future of humanity is. The second great colonization period of the planet is the age of exploration. Now, the Europeans rediscovered North America. Humans were already here. But if you look at the technology, how technology played a role in that, and how technology and exploration gave rise to empires, and the economic and social implications of that were really profound. So the compass, the sextant, the ability to navigate, the concept that the world is a sphere, and how do you navigate on a sphere? We're seeing knowledge advance, technology advance, and also humanity advance in terms of its scope and presence and mastery of a planet. It continues on in the 20th century, and we see, again, that technology is driving humans. We've conquered the planet. We've explored we've been, if not everywhere, we could go anywhere, anytime we wanted to on this planet, either directly or virtually, right? There's nothing that's inaccessible here. And again, tool building, technology is an important theme all along the way, from the Stone Age to the Iron Age to the Industrial Age, and now in the computer and information technology age. Humanity continues to grow, not only in terms of the scope of the knowledge that we've accumulated, our ability to apply it to solve problems and create a better life for ourselves, but also it's created more problems, created potential problems that we have to solve too. So look at global climate change, the impact of the human population on the planet, approaching potentially 9 billion people by the year 2050. What is the carrying capacity of the planet for the human population? We don't know what that number is. We may have already be above that number. We already may be potentially degrading the environment and reducing the ultimate carrying capacity. So these are all important ideas and considerations when you consider this path, this journey that humanity is on. In the middle of the last century, the dawn of the space age, born out of the Cold War, this sense of tension and conflict at a global level between great nations in this era drove humans to explore space and move out into space. I've had the opportunity to work a lot with the Russians and the Russian Space Agency. If you go to Russia, even today, Gagarin, I call him the Gagarin. He's the god of the Russian space program. The Soyuz rocket still launches from the same exact launch pad that Gagarin launched from. The same train that pulls the Soyuz rocket out of the vehicle assembly building. The day that they launched Gagarin, the front left headlight was burned out on that train. They have not replaced that headlight today out of just respect for Gagarin and the impact and the importance of that particular giant step that we took. And later the space race and the competition between the United States and the Soviet Union, East versus West, ultimately culminated in humans going to the moon. So we're able to go for a short period of time and explore several missions, and we know about the tradition of Purdue and space exploration and the lunar missions. It's a very proud tradition that we have here, and we hold that with high esteem in the United States still today. But where do we go from here? How do we get there? And what are we doing now? And what are the key technologies that we're going to need in order to really project human space flight exploration beyond these little camping trips to the moon? Now we're talking about a vacation trip to Mars. Are we really serious about becoming a spacefaring species? And then at the same time, it's important to consider how the technologies we're developing that would enable us to do that can actually benefit and protect life on this planet And I want to try to do both of those things at the same time in this talk. So right now, it's kind of like this is the truck stop for space, the future of human space exploration and a spacefaring species, International Space Station. It's been operational for about 15 years now. And this is a record. Humans have been in space continuously throughout the entire time of operation of the International Space Station. Really, in some ways, it's unprecedented where we're at now in terms of our capabilities and what we've been doing in terms of day-to-day spaceflight operations. This is intended to be a laboratory to develop the technologies and develop the countermeasures for a human mission to Mars. That was one of the big selling points politically that led to the funding for NASA to be able to do this. We still face tremendous challenges in terms of human biomedical countermeasures that need to be developed. Some of you may be aware of the one-year mission and the twin study with Scott and Mark Kelly. Those are really important biomedical research projects that we directed through the Human Research Program during the time I was at headquarters. Those types of studies are going to be really instrumental in developing these type of countermeasures. But at the same time, what we learn about humans in space and how the human body adapts to the stress of the spaceflight environment can be applied back to solve biomedical problems for humans here and improve the quality of life for humans here on Earth. So that's our next goal, Mars. People talk about the 2030 to 2040 time frame. When they use that kind of language, that's double speak for we're not going. That's my experience from being in Washington. There's no budget for it. There's no political will to invest in going to Mars right now. So we're playing around. We're trying to do good science. We're trying to set the stage for next generation technology development so that we can go to Mars. But seriously, when people say 2030 to 2040 time frame, that's not by the end of this decade, is it? So, what is the future human space exploration? Now, this is a chart that was developed from headquarters, NASA headquarters in Washington, D.C., and you see that mostly what this chart is talking about space exploration centers on human spaceflight capabilities. So this is spaceflight capabilities. This is not really space exploration emphasizing, in my opinion. So space exploration, what is it going to take to get to Mars? Interplanetary transport. Well, we probably know how to do that. We could probably, if we can assemble a space station in orbit, we could assemble a big giant rocket and pack it up with a bunch of food and water and send some guys off to Mars. We send interplanetary probes out all the time. We've been doing that since the 70s. So we're not talking about new technology. We can do that. That's really something that's doable now. We need to develop landing and roving capabilities for a Mars mission. Again, we probably know how to do this already. This is not the cutting edge in terms of what's going to be required to have a successful Mars mission. Habitation. Again, we could probably figure out how to land materials and assemble materials. If we can build a space station in space with no gravity, we can probably build pretty decent little cabins and campsite facilities on Mars for people to go have little vacations for short periods of time. But again, that's what I'm interested in, and I don't think most people really consider to be the future for human space exploration. We were talking about becoming a spacefaring species and actually having long-term habitation. So we want to send people, not necessarily robots, because for, I think, several reasons. Because humans in the long run are going to be more efficient in terms of exploration and doing science in situ, decision-making capabilities. Now, we've heard a lot about the rise of the robots, and maybe someday we'll have robots that totally could replace humans and do robotic missions If we get to that level, we probably have other problems. Maybe we will need to leave the planet because the robot said, we don't want you here anymore. So maybe that's another reason why we should be developing habitation for human presence beyond this planet. So we want to explore. Again, this is something that's part of our DNA. It's part of our core essence of being human beings, exploring, discovering. We want to do it. So we need to develop the platforms in order to enable that. And we want to go to Mars because of the implications in studying and understanding the origins of life. Almost every Mars scenario and long duration human exploration scenario involves greenhouses, right? So we all saw The Martian and saw how the hero of the movie and the book survived by developing some ad hoc gardening and greenhouse capabilities. The movie was really accurate in terms of a lot of those aspects in the science in that regard, but it's going to take a little bit more than, at the last minute finding some potatoes and, recycling your, building your own little junior bioreactor with your waste materials to grow a garden at the level that it would take to support, really a human habitated mission to Mars. So we start to see these greenhouse modules for providing fresh food and vegetables for astronauts. But if you really start thinking about long duration habitation and exploration, we're talking about not just greenhouses to feed people, we're talking about more advanced biologically based life support. So the term bioregenerative life support or controlled ecological life support are terms that have been used in the past to describe efforts in these areas. So it's not really just a module that you can stick on and grow some plants in and have some fresh salads every once in a while. We're really talking about the technology that essentially replaces what the Earth does. This is our current bioregenerative life support system. Now, when you start miniaturizing it and creating modules to replace these types of functions, even on small scales, it becomes extremely difficult. These are tremendous engineering challenges because you're integrating biology and mechanical and electrical systems in really intricate ways that haven't been explored before. So there's tremendous challenges. The advantage we have here with the planet at the planetary scale is the large buffering capacity we have, the mass of the planet itself, a 1G environment with oceans to buffer pH, gases, temperature. In a small scale, we can approach some level of success in terms of a closed-loop bioregenerative life support system, but there's still tremendous challenges in terms of creating a technology that replaces what the planet would do even at that type of scale. So, for the since the 60s, 70s, 80s, 90s, up into the 2000s, if you look at the Soviet and Russian space program, the American efforts, and also collaborating with the Europeans to some extent, there's been some fairly extensive work in terms of bioregenerative life support capabilities. And again, the foundation technology for any bioregenerative life support system, and again, this includes food, water, atmosphere, and waste recycling, is plants. Photosynthesis for plants can scrub CO2, produce oxygen, so it can replenish the atmosphere. It's a source of food. It also, through the recovery of transpiration of water from the plants, you get purified water. So plants in such a system are going to be very important, the foundation for a closed-loop bioregenerative life support capability. A lot of this has been focused on NASA, but there was a lot of Cold War research in this area, especially from the Soviet Union. They were developing fallout shelters and bomb shelters that people could survive a nuclear war in, where they had built in these giant bioreactors with algae to replenish the atmosphere. So they were actually exploring that technology for more military applications. Again, the US Navy has also had similar projects associated with undersea and submarine operations. And also, too, there's been private investment and private projects. This is a Biosphere 2, which was the first private attempt at a large-scale closed-loop bioregenerative life support system. It had agricultural modules. It had modules that were represented all the ecosystems of the planet, and ultimately there were some design failures that led to some imbalances in gas inputs, and it led to the failure of the system. Doesn't mean that probably, not sure why they never did go back and try to develop countermeasures for the problems that they encountered the first time, lessons learned, and try to redo the experiment. But it was a gallant investment and tremendous first effort at the private level to start to develop these types of technologies. And again, I'm talking about bioregenerative life support for human habitation beyond the planet, but a doomsday scenario is that the planet's climate degrades to the point where we need these types of technologies for human survival on this planet. So this is just a couple of shots of the biomass production chamber. This was the centerpiece of the controlled ecological life support effort at NASA's Kennedy Space Center during the 90s and the 2000s. This was actually the giant vacuum chamber that they tested the Mercury capsule in as part of the Mercury program. They converted it into a sealed chamber and did these biomass, these plant growth experiments using, at the time, metal halide lamps. So you can see the white metal halide lamps, hydroponic systems, grew everything, tested everything from sweet potatoes to crops of wheat, leafy greens. Absolutely set the world's record for agricultural production in terms of plant productivity and crop productivity using these chambers. Around 2004, 2005 time frame, because of the changes in the political approach and political management of the space program. This is when they first really started seriously talking about going to Mars, but we hadn't finished building the space station. There was no new money coming into NASA. Over the years since the moon program, the share of the budget, the total budget that goes to NASA has been shrinking and shrinking and shrinking. So eventually, these facilities and the whole entire cells and bioregenerative life support effort from NASA were dismantled. The chamber was destroyed. The hangar, the building facilities were wiped out. They're gone. We totally lost those capabilities. Again, during the Soviet era, not only were they testing closed environments for life support, they were actually putting humans in and closing the loop and looking at crew performance, psychological factors, the whole package in terms of developing these types of approaches. All kinds of biomedical testing, and again, the foundation for a closed-loop bioregenerative life support for humans is going to include agricultural and plant production. So when you think about the future, the right stuff for the next generation space explorer, you're probably going to need to be vegan. So get used to that idea. Today, right now, probably the most advanced and the best supported effort in bioregenerative life support is from the Chinese space program. The Lunar Palace is actually a fairly large complex. It has plant growth modules. Again, plant growth and vegetable plant production is the foundation for the future for bioregenerative life support and human exploration. I think they just completed a mission where they put 8 students in for a year. So they're doing human factors, closing the loop. You can see here in this picture the purple glow are from the red and blue LEDs. These are optimized plant lighting systems for photosynthesis. This is technology that was developed initially out of Kennedy Space Center and the NASA effort. So now these technologies are being used by the Chinese to support their effort in developing similar types of technologies. They're investing in a space station. They're building rockets. They have a manned spaceflight program. They're making a lot of progress. They're coming on fast. And again, this is a fairly large complex in Beijing. So right now we've been focusing on the use of the International Space Station. One of the projects that we've had, again, NASA's scale and scope and work in this area has been greatly reduced. This occurred down in the time frame that there was a push to develop more commercial space, and the shuttle program was cut, and the budget was crunching the final assembly phase of the International Space Station. So NASA basically gutted the entire future of human spaceflight exploration in order to finish building the space station, and we really haven't fully invested in supporting the science that's required to use the space station today so that we can be competitive and we can project human exploration, US-led efforts in the future. But what we do have is pretty impressive. This is a picture of Commander Swanson. This is the first flight experiment with the veggie unit. Again, here's the red and blue LEDs, and he grew a crop of lettuce. Since this was the first crop of lettuce that was grown, we had food safety concerns. So they harvested the material, they brought it back, analyzed it from a food safety perspective, because we're still learning a lot about the human microbiome in engineered environments, and especially the microbiome of a spaceflight system. Where we know in space, previous research has showed that bacterial virulence tends to be enhanced in microgravity. So there's a food safety concern that bacteria coming from humans could be colonizing the crops and also may be becoming pathogenic to the astronauts. So we analyzed that. Turned out it was safe. And then the next grow out we did was during Scott Kelly's one-year mission. And here's a picture of the harvest. They also had, so they actually were allowed to eat the lettuces. So this is the first time a crop had officially been grown to support astronauts. There were reports from the Mir era, from the Soviet space program, that on occasion that some of the Russian investigators' plant materials were actually consumed by the crew, I think because they were bored. They ate the radishes on one particular experiment. So it's not the first time that vegetables were grown and eaten in space, but this is the first time it was actually planned. So we did provide them with a little bit of like a vinaigrette salad dressing, because you're not going to eat the lettuce on its own, and your palate does change in microgravity because of the fluid shifts. And then on the follow-up, the third round with veggie, we actually grew some flowering crops. And so one of the things that we've learned in the time that we've conducted plant experiments in space is that the crew that has the opportunity to tend the plants tend to get a lot of psychological comfort from that. I mean, you can look out the window, you can see the earth. So at least you have that kind of input, but actually having something green that you can touch and smell, that's alive, that you're tending, has a lot of psychological support for the crew. Imagine a crew in a completely sealed system traveling to Mars over a year-long period of time. We think that having plants in such a system would have a lot of benefit for the crew in those ways too. So this is a picture of the now infamous flying zinnia. Scott Kelly had tended this garden, this space garden, and he had taken this one particular zinnia out, and this is in the cupola. It's like a little covey with windows where the crew can sit and look out at the earth, and he had taken the plant and let it float there and took pictures of it. So I've been previously focusing on how these technologies are going to enable human spaceflight exploration and enable a future for humanity to project itself to become a spacefaring species. But we already face tremendous problems in terms of population. We already face tremendous problems in terms of limitations and reaching the limits of what our agricultural capacity is given the arable land on the surface of the planet. And with the growing population, growing cities, people are now moving to vertical and urban gardening. So here's some pictures of technology originally derived and developed by NASA, now being used commercially. There's a huge investment in Singapore at the national level. They've invested in supporting and creating an industry, vertical farming industry. There's companies, startup companies in New York, Chicago, big cities, a big effort in Japan called plant factories that are growing vegetable crops for a growing market. No pesticides, controlled environment, no pesticides, no herbicides, no transport costs to get the crop to the customer. So the business model is falling in place. And even with using artificial lighting, the red and blue LEDs are very efficient. They're right on the edge of being totally profitable right now. A lot of these companies are just persisting. But as the technology continues to invest and as the market continues to mature, we're going to see that this is a growing industry. Here's a picture of a facility in Australia that was developed, and a picture of what we might see in the future. Integration of green technologies. So this is the utopia that we envision for humanity on the planet by embracing the idea of bioregenerative life support, first conceived to support humans to explore off the planet and to live off the planet, applied back to a better planet. And we see this over and over again. That's one of the values of exploration and challenging ourselves as humans to go do these incredibly hard things, is that along the way, we have to develop new technologies. We have to solve problems, and that leads to new technologies and new solutions for problems that we face here on Earth. So this is the future we hope for life on planet Earth. We hope that we can augment our ability to explore using bioregenerative life support capabilities in controlled agriculture. Again, here's an artist's rendering showing an exploration outpost with crop production on the moon. Colony scale terraforming level bioregenerative life support, closed loop life support capabilities may be a possibility in the future for permanent outposts and industrial level human habitation in areas where there may be economic value or economic drivers that are creating the vectors to drive humans to explore. But again, in a doomsday scenario, if the planet were to become inhospitable planetary body, these are the same types of technologies that may allow humans to persist, at least. And then there's the idea of multi-generational exploration and human habitation over long periods of time. And again, these are great artist renderings. I love seeing how the artistic eye and the artistic mind can mold and shape our vision for what we want to do in the future. I think it's very important that we include the arts in our vision of what we want to do scientifically in engineering and technology development in the future. It's good to use your imagination. So here we are today. We've basically conquered this planet. We've colonized it to the point where we're now creating our own problems. And we have the opportunity to solve those problems if we come together as a species and acknowledge that we have problems so that we can build on our tradition of exploration, of discovery that has driven our species from the beginning and driven our evolution to a future where we hope that we are exploring and colonizing and conquering other planets for the human species. So I think this is another artist rendering that kind of summarizes the human existence through the age of exploration out into space to this future that we don't know what it might bring in terms of the benefits for that we gain from human spaceflight exploration. But I think these are important challenges for us to face as a species, because even if we don't achieve all of our goals in terms of space exploration, surely along the way we're going to develop technology and approaches that are going to be really important to support humanity and help us solve problems here on the planet today. So thank you very much for your attention, and I'll be happy to answer any questions.
Do you have any questions?
This is Laura. I love that Carl Sagan slide. So you hinted at it a little bit, but in your opinion, what is our best bet at motivating humans on Earth to explore space a little bit? There's like pissing contests with Russia. There's economic, you want to mine the moon or mine asteroids, or maybe you want space tourism. But like, what do you feel like, knowing today what we know, what's the best bet for motivations? Thanks.
So during the time I was at NASA, one of the big areas of friction we had to deal with was promoting and supporting basic fundamental science, which is a process of identifying unknown unknowns. Right? So we're going out where there's nothing, and hopefully along the way, and that's how science really works, right? Versus the idea of, we should only be doing the research in space that has a commercial outcome. So quit doing the research over here that we don't know what's going to happen. Just do the important stuff. You know, it's so easy just to see how, what's going to lead to something commercial. Just do those things and not do the basic science. And that's a real area of concern, because it pulls us away from the fundamental science that we need to do in order to do exploration. It also pulls us away from the discovery of the unknown unknowns, right? So that the next opportunities are going to come from this major new discovery because someone was doing curiosity-driven science, right? So in terms of motivating our nation politically, or motivating a species to come together to invest in these types of activities, but I've heard before other people say that the best bet we have is if aliens attack from another planet. The Cold War really was a tremendous, that whole competition with the Soviet Union was a tremendous driver. We would not be where we're at today in terms of space exploration if it had not been for that. I'm not sure we want to start a new Cold War, or it'd be nice if we could figure out a way to work with the Chinese. They are not active as partners on the International Space Station. They tend to do their own work right now. They collaborate with the Russians, but the Russians collaborate with us on the International Space Station. The Chinese are also collaborating with the European Space Agency. And we've cut ourselves out of that. We can't do a true multinational effort at this point because of the political environment that we're in. So it's outside of the idea of competition and this space exploration as this friction in this Cold War zone, I'd like to think that we wouldn't have to go back to that kind of scenario in order to advance the human efforts in these areas. And then we can come together under the auspices of something greater. But I just don't see that happening in the near term either. But it's about educating people and having people be aware and understanding how the drive to explore and how that has led to all these benefits. Computer technology, all the things that we're talking about in this conference that are potential downfalls for doom probably had their roots in the space program in terms of computing technologies and materials and integrated circuits, and all spun out of the Cold War and the Department of Defense and the space program.
Thank you for the talk. Do you know what kind of biological experiments or projects in the near future are going to space, like on the Mars 2020 mission, or just other future experiments that are coming up soon?
We just completed the one-year mission with Mark and Scott Kelly in the Twin Study. That's actually probably one of the most important biomedical research projects ever to be conducted, because of the way it was designed. We used a basic and integrated omics approach, so really the best of the best in terms of modern new technologies for systems biology. Moving towards systems biology and open science architecture for supporting space sciences was one of the things that I championed during my time. That's really going to be key. You can go Google NASA Gene Lab. You can download spaceflight data from an experiment that looked at mouse liver of mice flown in space versus ground and look at 30,000 genes. And if you can identify a pathway in there, you can publish a paper. Open science. The Advanced Plant Habitat is getting ready to launch the next SpaceX. That will be basically the veggie unit, but a really high-end research with really high-end research capabilities. Veggie right now is a demonstration unit for vegetable production, but we still have a lot to learn about how plants sense and respond to the microgravity and spaceflight environment. So those will be some of the next steps. We have a microbial observatory initiative that was put together over the last few years that is going to look at the microbiome of the engineered environment of a space station to try to understand how bacterial populations change and how what types of countermeasures and threats and issues that we need to look at in terms of long-term human habitation in that regard also.
Do we have any other questions?
So I'm Dave Mosher with Business Insider. One fascination of our readership is Elon Musk, and he's very outward with his long-term plans to colonize Mars. Just fill my ear a little bit about that from your perspective. Is he crazy? Is he trying to undertake something that is just insanely difficult and has really no hope of happening under his auspices? Or does the world kind of need somebody like Musk to whip us all into shape and maybe motivate some of the basic research? I don't know. What's your perspective?
Well, if you look at the reusable rocket concept and having that recently been demonstrated, that's a huge game changer in terms of space program, because now you have now we are approaching low cost launch capabilities because we can reuse rockets. We could assemble space exploration capabilities in orbit and launch a mission from Mars to there. So, and when I talked before, interplanetary transport and landing capabilities and modules to take people there and do a camping expedition on Mars, that's all within our grasp. That's not really new technology, but his idea about colonizing, and that's going to require investment and greater investment in the area of the bioregenerative life support capabilities and controlled environment agriculture in those types of scenarios. I think he's done great things in terms of his impact on the space program because of his philosophy and approach that he's developed. And also, too, if you look at what he's done around the IP domain of the IP that his company has developed, they just make it available. They don't license it. He's trying to do everything he can to grease the skids in terms of human exploration.
What are some challenges related to closing the loop on components and hardware that might break in space and you're millions of miles from Earth? Would 3D printing be the answer to that, or how are we going to fix that problem?
Yeah, in the past it's been a redundancy issue, so you just have multiple backup systems. But recently they did have installed a 3D printer on orbit on the International Space Station, and they are touting that as a source for potential replacement parts. Biological systems are really resilient. They tend to be self-healing, self-repairing. So that's one of the advantages of a bioregenerative life support capability. You're not going to see probably a complete bioregenerative system that doesn't have backups that are physical chemical. And there is some imbalances in terms of the inputs and outputs for carbon, for example, in a closed loop system, because you don't ever really fully recover all the carbon from the biomass. Even though you recycle it, you may end up with some ash or some other types of materials like that. So there are some slight imbalances, but even if you had to stow some materials to account for those imbalances. The fact that you're recycling everything else starts, and the mass of the bioregenerative life support system versus carrying everything you need, the numbers start to really shift in favor of the bioregenerative approaches, which is a shame when you consider that NASA's investment in that area is so minuscule right now.
Let's give Professor Porterfield another round of applause. Thank you.